In the first part of the history of the atom, we wrapped it up with J.J. Thomson's model, the plum pudding model, where the protons and electrons were evenly distributed throughout the atom, and um, they'd only discovered the protons and the electrons. Now we're going to look at why Thomson's model was wrong. Ernest Rutherford was actually doing experiments to try to prove Thomson's model correct, and he ended up proving it incorrect because of the results and the evidence that he actually found. He did what was called the gold foil experiment. He took alpha particles and he shot them, which alpha particles are large positively charged particles, and he shot them at gold foil and had the counter behind it that would just record how many particles showed up in which areas. Well, again, they thought that the atom was a solid pudding type material, and so when he thought that he shot these alpha particles at it, then you should get, when it comes up to a positive and positive, it should just repel. Um, what actually happened when he shot the alpha particles at the gold foil, the majority of them went straight through and did nothing. So that in itself changes the model that Thomson had. Thomson's model of it being this solid pudding-like matter could not be correct. It had to basically be empty space. There were a few of the alpha particles that were deflected off to the sides, and some came straight back. And so he knew there was some positively charged portion, but it wasn't scattered throughout like they thought. It was all condensed and right in the center in one spot. So it was only if it came in contact with that dense center would it be deflected or bounce back. This is what the gold foil kind of setup was like. The detector, this on the outside, was what would count the particles as they passed through or were deflected off. And this is the source. It was a lead container. And then in here was the source of the energy that would shoot out the alpha particles. If we look at this, it doesn't look like they're going to play, so we're going to skip that. And we'll look at the gold foil videos in class. So what was going on? Most alpha particles went straight through and the detector picked them up. What were they bouncing off of? What was causing these positive particles to repel? Well, according to Ben Franklin, it had to be something positive. And with Goldstein and Thomson's work, they understood that there were positive and negative particles in the atom. So Rutherford was able to look at it and say, okay, if these large positively charged particles are bouncing off of something, it must be that all of the positive charge is concentrated in the center. And he called this the nucleus. So, where where he took the model from J.J. Thomson, that was the plum pudding model, that is like a blueberry muffin or a chocolate chip cookie, where the blueberries spread throughout the muffin are the negative portion and everything else is positive, he said that can't be how it is. There must be all of the positives concentrated in the center of the atom, and then basically the whole thing's empty space with the negative electrons on, on the outside. This is when the model changed and it became the nuclear model. So it now has a nucleus with protons in the center and the electrons on the outside. So if we look at this model, it makes us question though, okay, Ben Franklin's already shown us that like charges repel. So if all of the positive particles are in the nucleus, if they're right by each other, they should just repel off of each other and the atom should explode and it shouldn't exist. So that led then to the discovery of the neutron. And the neutron is like the glue of the nucleus. These neutral particles are in between the positive particles so that the positive particles will not repel each other and explode the nucleus of the atom and destroy the atom itself. So that's why the neutron's job is basically like the glue, what keeps the atom together. If we compare the size of the nucleus, if you took a small little green pea and you set it on the pitcher's mound in Busch Stadium, and then on the outside of the stadium drew a ring, that's where the electrons would be. And that's how large the atom's volume would be as compared to that little pea on the pitcher's mound that is the nucleus of it. And that little p would hold 95.9% of the mass, even though the volume of it is goes all the way out to the outside ring of Busch Stadium. So, what did Rutherford discover? He discovered the nucleus. The positive particles were all in the center. And just as important, he discovered that the atom was not a solid pudding-like material. It was mainly empty space. This was not the final model. We still obviously have a lot to go through to get to what our current model looks like. So the next portion that came up was by a man named Bohr. He was working with Einstein on with light, and he figured if they worked with hydrogen, since hydrogen has one proton and one electron, then hydrogen should give off one color of light. So they took hydrogen and they ran electricity through it, and it will give off a color of light. Just like the neon lights that we see now, that's what they were working with. They're called spectrum tubes. And it gives off the light for that particular element as electricity excites the electrons and they move. Well, that's why they chose hydrogen. They're looking for one color. When they actually pass the light through the prism, it's separated into four different colors of light. So this made him think about Rutherford's model of having this single ring with all the electrons in it. If there was only one electron and it was just in this one single ring, then there should have only been one color, not four different colors of light being given off as they viewed it through a spectrum, or excuse me, through the prism. They knew something had to be different to the model. So this is what led then to the orbitals. Orbitals are energy levels, or levels where he thought the electrons are orbiting the nucleus. Just like planets, he envisioned that each electron had its own energy level, and then they could, when energies added to it, like electricity, gain energy and jump further away into these other orbits. This model is called the planetary model because he really thought that the atom just mimicked our solar system, that the nucleus was acting as the sun, and then the electrons were rotating around it. So it was given the name the planetary model because he thought that it was just mimicking what we see there. Bohr explained that as it gains energy, then that electron is going to have to also lose it to fall back to its ground state, or the state where it's not excited at, doesn't have extra energy. And when it falls, that energy has to go somewhere. So where does that energy go? It's released, and our eye detects that as light. So if you have an electron, electricity is ran through it, it jumps out to an excited state, and then it could fall back and give off energy, and the energy then is given off as a wave that our eye then detects as a color. So the shorter the drop, then you have a wave that has a lower frequency, a larger wavelength, and you see colors that are in the reds. Then the higher the jump is, so when it falls back down, it's giving off a greater amount of energy, then you see colors in the blues and the purples. So we can look here in the visible series, and we can see the electron could fall from just one energy level to its ground state, or it could fall from 2, 3, or 4. So we were actually seeing a red, green, blue, and a violet color. And that doesn't include the things that we can't see, because these are all light. Just the colors are our visible portion that we can detect. So different substances do give off different colors, but why does this happen? It's not just based on how many electrons they have, but it depends on how many jumps those electrons can make. This gives you a spectrum of some different elements. Helium has 2 electrons that are jumping. So you get more bands than the hydrogen one that only has 1 electron. Carbon has 6 electrons, and you get more jumps that are possible to give off energy. And then neon has 10. And here you can see the more jumps, the more wavelengths that are hit, and you get more line spectrums for that particular element. So our model has gone from the marble model of Democritus and Dalton. It's changed to the plum pudding model of J.J. Thomson, to the nuclear model of Rutherford, to now we have the planetary model of Bohr and Einstein. So Bohr's model shows a nucleus and electrons in each energy level. We now know that every electron does not have a single orbit that it jumps in between, but that it has a region of space. So we don't call it an orbit anymore, we call it an orbital, which is a region of space that it spins in. Because it's not this two-dimensional model that's just flat with a ring, it's a 3D model. So it has these regions of spaces that electrons spin around in. The first energy level is so close to the atom that it can actually only hold 2 electrons spinning around in this area. The second energy level is larger and it can hold 8. The third can actually hold 18, and then the fourth can hold 32. There are more energy levels than just 4, but everything from the fourth out, we know can hold a total of 32. Can they hold more? Possibly. The elements that we've discovered so far only show us with a maximum of 32 electrons in one particular energy level. So all of our models, the marble model, plum pudding, the nuclear model, the planetary model, and then obviously we've made other advancements, and since 1913, in the 20s, that's when we were able to discover and learn about orbitals, and now we've moved to looking at how electrons can act like waves and give off light and act like a particle and a wave. So our current wave model is somewhat different, and you can see here it shows you the more as like a cloud, like fuzzy areas, because to be able to find the electrons, you have to hit it with energy. Well, when you hit it with energy, it changes its location. So from the experiments that we can do, we see movement of them that give us this real fuzzy outside of the the nucleus, and that's where it got its name to be the electron cloud model. So why should we even know about the atom? The first thing is it originally was thought that it didn't exist, that we weren't made of anything. It was just the whole world was one continuous piece. What really drove the government, though, was a little thing called the Manhattan Project. They knew that if something so small could contain such great energy, there had to be a way to harness that. Well, they put lots of money into the project, and Einstein and his team worked, and they did develop the atom bomb. Now we have a weapon that Einstein says he wished he had never helped create, and we have disasters that we now look back on in history that the US has used the nuclear bombs and seen what can actually happen. Um, and we'll look at these videos together in class. So the push was for something to have that control and that power that was so great. And once they captured it, now we're spending the rest of the time trying to convince people to get rid of it and stop the nuclear weapons and to just contain them and get rid of them. So, with the power of something, we can have control, but it may not always be exactly what you would expect.